Okay, we're going to skip ahead a few chapters to chapter 30. The last chapter that we finished was chapter 26 on magnetism. So we learned a little bit about magnetism, and prior to that we had learned a fair bit about electric fields. So we know about electric fields and magnetic fields. And at the very end of the last chapter, I introduced electromagnetic waves. And there's lots and lots we could say about electromagnetic waves. We know a little bit about electromagnetic waves because you know some amount of about magnetic fields and electric fields. And electromagnetic waves are composed of electric and magnetic fields. So there's lots more we could say about that, but we don't have time, so we need to move on to this last section on reflection and refraction, and we're going to be considering electromagnetic waves. Okay, so we're going to look at the behavior of electromagnetic waves and in the context of these two phenomena, reflection and especially refraction. Okay, so reflection, what can you say about reflection? Well, it's illustrated nicely in these pictures on this slide, slide number 2. If you have a reflecting surface, so here's a surface here, and you imagine a ray, a little tiny beam of light, which is an electromagnetic wave. If you have a ray of light and it hits a surface, if it reflects off the surface, it will reflect in this direction. Okay, so some of this electromagnetic wave that is the incident ray may get absorbed into the material, but you may get some reflection as well. And the important thing to note about reflection is that this angle we call theta 1, and this angle we call theta 1 primed. The angle of incidence and the angle of reflection, it turns out that these are equal to each other. Okay? If we have many rays of light that are coming, striking this flat surface, and these rays of light are initially parallel, then because in each case the angle of incidence is equal to the angle of reflection, all these reflected rays will also be parallel. Okay? This is the kind of reflection that we care about, okay, and it's called specular reflection, okay, and it's when, as we said, when parallel rays reflect off a smooth surface and stay parallel. Obviously, if you have a bumpy surface like the one shown in figure C, then the way the light gets reflected, it will kind of get scattered in many different directions. We're not going to worry about this so-called diffuse reflection, only specular reflection. Okay, so that's reflection. Now let's go to the more interesting phenomena of refraction. Okay, so the starting point here to understand refraction is it's all about the speed of light, okay, or the speed of electromagnetic waves. So you'll often see this number written down that the speed of light, or the speed of any electromagnetic wave, is 3 times 10 to the 8 meters per second. And that's a fundamental constant of nature. It's fixed, just one number. But what you have to appreciate is this is the speed of light as it moves through a vacuum, as it moves through nothing. If light actually goes through any other medium, or any medium, so if the vacuum is filled with some stuff and the light goes through that stuff, you can measure the speed of light in that medium and you'll discover the speed will be less than the speed of light in a vacuum. Okay, so we'll use V for the speed of light in any medium other than a vacuum, and C is the speed in a vacuum. So we define something called the index of refraction for that medium that has light traveling with this speed V. And the index of refraction is a number n, and it's defined to be C divided by V. And because C is always bigger than V, n is always bigger than 1. Okay? So this number, this index of refraction, is unique to every different material, any different substance. So here's a table of values of indices of refraction for some common substances. The important ones I would say are, the first one is air. What you'll notice is the number is very close to 1, slightly bigger than 1, but close to 1. And what that's saying is that V is very close to C. It might be a little bit slower. Light might travel a little bit more slowly through air than it does through a vacuum, but not by very much. Usually we just approximate this as 1. Other important ones are water. Okay, so we have an index of refraction of 1.333. So light definitely does travel slower in water than in air or in a vacuum. And so these are some liquids, and then solids. The important one, I think, will be glass. Okay, now glass isn't just one substance. There's many different types of glass. So depending on what kind of glass you're talking about, you might have indices of refraction that vary between 1.5 and 1.9. Remember, the bigger the value of n, the slower light travels through that medium. Okay, so what effect does this have, the fact that light travels slower in a medium than it does, for example, in a vacuum, or that light travels at different speeds in different media? Okay, so let's look at this picture over here, and we're looking at an electromagnetic wave, which we kind of visually depict with a sinusoidal wave. So it's just a wave of a single wavelength and a single frequency. Okay, so its wavelength is lambda 1. Its speed or velocity is v1 to the right. And the 1 is just, well, we're looking at medium 1. Medium 1 might be air, or it might be water, or whatever. Okay. And then there's an interface here. And at this interface, we go from medium 1 to medium 2. We might be going from air to glass, or from glass to water, or something like that. And so there's a different speed or a different velocity. It's still going to the right. And what we find generally is the wavelength will change. Okay, how does the wavelength change, and how does the change in the wavelength depend on the indices of refraction? Okay, so the important thing to note is the frequency of the wave in medium 1 and the frequency of the wave in medium 2 are equal. Okay, the frequency does not change. The speed changes, and it turns out the wavelength changes, but not the frequency. Okay, so how do you think of the frequency? Imagine that you're an observer at this point A, and as the wave propagates to the right, you're counting the crests as they go by. Okay, here's a crest, here's a crest. All of these crests are moving to the right. Okay, and you count how many crests go by in a given time. And you might find there are 10 crests per second or per millisecond or whatever it is. Okay, that will simultaneously be the rate at which these crests intersect this interface between the two media. If you measure 10 crests per second going by at point A, there will be 10 crests per second slapping against this interface between medium 1 and medium 2. Okay? And if you're an observer at point B in medium 2 and you're counting the crests as they go by, well, what do you notice? You're going to see wave crests emerge from this interface at whatever the frequency was that these wave crests emerged from this interface. Okay, so the frequency then, we're arguing, of the wave in medium 1 and in medium 2 are the same. Okay, so let's consider the wavelength of the wave in any medium. And what you discover is the wavelength is the speed divided by the frequency. Okay, we've seen that fundamental equation before. But v is the speed of the wave in the medium. Well, that's equal to c divided by n, speed of light in a vacuum divided by the index of refraction. And okay, so c divided by f, that would be the wavelength of the wave if it were traveling through a vacuum. So we'll call that lambda sub vac. Okay, it's the speed in a vacuum C divided by the frequency. And the frequency, remember, doesn't depend on what medium you're in. That's fixed. Okay, so let's see. So that means the wavelength in any medium compared to the wavelength in a vacuum is going to be less. Okay, because n is a number which is greater than 1. So you can kind of think, if you want, medium 1 could be a vacuum. Doesn't have to be necessarily, but just to help us understand this derivation over here, think of this as the vacuum. Think of this as some non-vacuum medium. And we see a shortening of the wavelength relative to the wavelength in the vacuum. Okay, so what comes next? Okay, let's consider, again, a ray of light, thin beam of light, which is incident upon some surface. Okay, what happens when light strikes a surface? Well, we can get reflection, and we know the reflected ray will move off at an angle with an angle of reflection, theta 1 primed, measured with respect to the normal. So this dashed line is normal to the surface here. So the angle of reflection is equal to the angle of incidence. So we've seen that before. So some of the electromagnetic waves, some of the light gets reflected, but some of it will go, generally speaking, some of it goes into the medium. So if this is going from air to glass, so medium 1 might be air, medium 2 is glass. Some light, of course, gets reflected off the surface of the glass. Some light goes into the glass. Okay, and this ray here, this portion of the light that goes into the second medium, medium number 2, we call that the refracted ray. And it turns out this angle theta 1 and this angle theta 2 are not equal. Okay, generally speaking, they're not equal. It tends to be the case as you go from a more dense medium, from a less dense medium, like this could be air, into, let's say, glass. Glass has a much higher density than air does. It tends to be the case that the refracted ray will bend towards this normal line here. Okay, so in other words, it will end up being the case, typically, that theta 2 is less than theta 1 if you go from a less dense to a more dense medium. Generally speaking, or more generally speaking, it's when you go from a medium with a lower index of refraction to a higher index of refraction that theta 2, the refracted angle, or the angle of refraction, will be less than the angle of incidence.